Hello again, Physics 30s. In today's lesson, we are going to wrap up all of the content for Physics 30 by talking about quark theory. Learning outcomes are to describe the modern model of the proton and neutron as being composed of quarks. And two, we're going to compare and contrast the up quark, the down quark, the electron, and the electron neutrino and their antiparticles in terms of charge and energy. And three, describe beta positive and beta negative decay using first generation elementary fermions and the principle of charge conservation, where Feynman diagrams are not required. If you'll recall, the Feynman diagram was the illustration on the first slide of the quantum field theory lesson, which I told you to ignore. So we don't care about them right now. Quark theory. Quark theory tells us that all hadrons, so remember, hadrons are heavier particles, the heavier subatomic particles, that includes both protons and neutrons, are made up of a cluster of two or more particles called quarks. So what that's saying is that you can actually take a proton and a neutron and you can break it into smaller building blocks. And the building blocks that make up protons and neutrons are what we refer to as quarks. Now you might be wondering, like, where did physicists get the idea that maybe a proton or a neutron was made up of smaller parts? Well, I'll drastically simplify the idea here. So let's say that we have a proton. And what I'm going to do is I'm going to fire some charged particles at it. And so if I fire a charged particle like this, it comes to the proton, I'd expect it to maybe deflect up and away. No problem. Proton's positively charged, this guy's positively charged, they should repel. Maybe I fire another one, comes near, and then once again it deflects. So great, no problem. And then, let's put another one down here. I fire another one, but instead of deflecting, it actually comes a little bit close to the proton, which is weird because it's like a proton's a positively charged particle. So if I fire a positive charge at a proton, how could it attract to it a little bit? So I believe it got physicists thinking that perhaps there's a part of a proton that might actually be negative. So we're going to have to dive deeper to figure that out. Okay, properties of quarks. Quarks interact primarily by means of the strong nuclear force. So you'll recall from the last lesson that the mediating particle for the strong nuclear force was a gluon, and the point of a gluon was to ensure that protons and neutrons are locked together in the nucleus. Since protons and neutrons I've established as being made up of quarks, they also interact by the strong nuclear force. Here's where I don't get like what physicists are trying to do here. So instead of saying there are two types of quarks, they say there are two main flavors of quarks. Again, the sense of humor is a little bit beyond me in terms of why they decided to call it this. There's two main quarks. We have an up quark and we have a down quark. We'll abbreviate an up quark with U and a down quark with D. Now, the interesting thing about these quarks is they actually have a fractional charge. An up quark has a fractional charge that is positive 2/3 times the elementary charge, and a down quark has a fractional charge that is negative 1/3 the elementary charge. Okay, this is going to be important in explaining, well, how can a positive charge get attracted to a proton? Well, it's got to have at least one down quark because it needs to be attracted to it. I should mention there are 4 other types of quarks as well, although we're not going to discuss them in here because I believe these quarks decay very quickly into like your up and down ones. We have a strange quark. we have, I think it's the charm. I was thinking lucky, but I think that's just a cereal, Lucky Charms. We have the top quark, or I think they call it the truth quark. And then we also have the bottom quark, or I think it's the beauty quark. Anyways, we don't really care about these four. We're just going to focus on the two stable ones, which is an up quark and a down quark. These are the fractional charges. You can also find those fractional charges on the formula sheet for Physics 30 for your charge of, I think, first generation fermions. Oh no, not again. Okay, we're going to come back to spin briefly. Each quark and antiquark has a spin number of 1/2. And you'll recall that a particle that has a spin of 1/2 means that you need to rotate the particle by 2 revolutions for it to come back to its original orientation, which again makes no sense. If you want to figure out what the total spin number is of a composite particle, you take all the individual spin numbers and add them together. So what that means is if like a composite particle contained 3 quarks and each quark had a spin of 1/2, to get the total spin number for your composite particle, you just add all the individual quark spin numbers together. Okay, let's focus more on charge, because charge is at least something that makes a bit more sense. Each quark has a fractional charge. It's either -1/3 or +2/3 of the elementary charge. And I've already identified that it's the down quark that has a fractional charge of -1/3. And we have an up quark that has a fractional charge of +2/3. When you take all the individual quark charges and you add them together, it must add up to be an integer charge. Okay, so you might have been wondering right away, like, wait a second, we made a big deal about in the electric forces and fields unit about how charge is quantized. Which means that the charge of an object must be a whole number multiple n of the elementary charge. Okay, it can't be anything smaller than that. Well, the quarks themselves can have fractional charges, but whenever you add up a cluster of quarks together, it will always be an integer charge. And we're actually going to talk in a moment about why you can't have an individual quark. Okay, so here's a diagram that shows the quark configuration of both a proton and of a neutron. So a proton has a quark configuration of U, U, D. So let's confirm this. What happens if we add all these fractional charges together? Well, fractional charge of an up quark is +2/3, the elementary charge. Fractional charge of my second up quark is +2/3, the elementary charge. And then the down quark has -1/3, the elementary charge. So when I add these all up, 2/3 plus 2/3 minus 1/3 would be +3/3, which is just +1 elementary charge. Okay, so it still works. Okay, as long as you add up all the individual quark charges together. Well, how about the neutron? So you can see here, the only difference between a neutron and a proton is that a neutron has a down quark instead of an up one. So it has a quark configuration of UDD. If we add these charges together, up quark has a fractional charge of +2/3, the elementary charge. Down quark -1/3, the elementary charge. Other down quark -1/3, the elementary charge. So you'd be going +2 minus 1/3 minus 1/3, and that would be equal to 0, which is the total charge of what a neutron is. Okay, now, a couple things. So the first thing is, you may have noticed in the picture that it actually shows the quarks of having color. So you have like blue, red, and you also have green. Now, back in the light and optics unit, we talked a little bit about what happens about when you combine these three primary colors together. So if you go blue plus red plus green, these are colors of light, not color pigments. Color pigments subtract to give you darker colors. Light colors add together to give you white. So when you take all the different colors of the individual quarks, they have to add up to give you net white. Okay, it's got to be a net white color. Now here's the thing. Do these quarks actually have color? And by color, do I mean like, is this red quark, up quark, emitting visible light with a wavelength of 700 nanometers? No. In fact, this whole concept of color dealing with quarks has absolutely nothing to do with color in terms of like colors the way we interpret it. It's another one of these really strange quantum properties that we can't really provide an analogy for. The idea, though, is that even though they aren't truly colors, if you take these quote unquote colors and add them together, they need to give you a net white color. Now, this is why you can't have a fractional charge on its own. So, for example, you can't just have this up quark here sitting by itself. If this up charge here was sitting by itself, like it would have a fractional charge of positive 2/3 the elementary charge. Okay. Now that defies the fact that charge is quantized, because like my lowest composite charge should be the elementary charge. So this color theory would tell you this is not possible, because if you have a blue quark on its own, it doesn't add up to white, and all colors of your quarks need to add up to white, even though it has nothing to do with color. Okay, you got it? Good. Second thing. You might think, okay, wait a second, maybe I could try to isolate one of these quarks. So let's try to separate one of these guys here. Now, these quarks are locked together by means of like the mediating particle, the gluons. The gluon is responsible for the strong nuclear forces holding it together. So you might be thinking, okay, well, maybe I can separate it. All I got to do is overcome that strong nuclear force. If I put in like a ton of energy to free this guy right here, okay, so I'll put in a ton of energy, overcome the strong nuclear force, and I'll free this up quark. So now this up quark is over here. It turns out in the process of doing this, in the process of like supplying energy to overcome a strong nuclear force, this energy would actually form mass. What mass would that form? Well, whatever up quark you removed, the energy used to do it would actually just fill in another up quark. So you're back to having this quark configuration of 3. And the quark you separated, whatever energy you put in to separate, would also produce a couple of other quarks. So then you're back to just having a quark configuration of 3, a composite particle. So it's weird. It's like in your effort to confine the quark or get it isolated by itself, the amount of energy required to do it and separate it would actually create new mass, and that new mass would just fill in the gaps in terms of quarks, and you're just left with a composite particle again. Okay, let's keep going, because if we stop and think about this too much, our brains are probably going to explode. Okay, now we're going to redefine what a hadron and what hadrons are in a little bit more detail. So we've already identified hadrons as being heavier particles, and hadrons are made up of quarks. We can take hadrons and we can actually break them into 2 groups. We can break them into baryons, and I believe we discussed what a baryon was last time. And I think a baryon was a hadron with a half integer spin. Yes, okay, so I got that right. It's a hadron with a half integer spin. Baryons are composed of 3 quarks. Antibaryons would be composed of 3 antiquarks. So in terms of what it would be some examples of some baryons, so what kind of composite particle contains 3 quarks? Well, that'd be my proton and my your protons and your neutrons. They're composed of 3 quarks, okay? And they have a half-integer spin. And the antimatter equivalent, the antibaryon, just consists of 3 antiquarks. We also have mesons, and I believe mesons were hadrons with a integer spin to them. Yep, an integer spin. These are composed of 1 quark and an antiquark. Okay, so one little example of this is a meson could be a quark, like an up quark, and it would have an anti-up quark. Up quark, anti-up quark. If I take these 2 spin numbers and I add them together, so the spin number of every quark is 1/2, so you'd have 1/2 plus 1/2 would just be equal to 2/2, which is 1. So you have an integer spin as a whole for the composite particle. If we go an up quark plus an anti-up quark. So because we have an even number of quarks, we can get an integer spin. For these ones, like for example, if you had like a UUD, so that would be up quark is a spin of 1/2. This has a spin of 1/2. If you have an odd number of quarks, like you have 3 for a baryon, that's going to give you 3/2. So that's a half-integer spin to it. Okay, I want to mess with your head a little bit more, just because this is fun. Okay, so wait a second. Let's go back to this whole idea of color. you know the property that we call color that has nothing to do with actual color. Okay, so wait a second. Let's say that this up quark had a color that was red. This needs to be added to the color of the anti-up quark, because the net color must also always be equal to white. So no problem for the baryons. It'd just be like green plus red plus blue equals white. But what about red plus blank equals white? What do you think the missing color is? If you guessed anti-red, you are correct. What's anti-red? I don't know. It's definitely no color I know of. But like I said, this whole concept of color really has nothing to do with the way we interpret color. So yeah, it's red plus anti-red is white. Okay, so what have we got here in terms of summary of this table? We don't really care, but yeah, okay, so I said up quark, you got down quark, strange quark, charm quark, bottom or beauty, top or truth quark. Up quark, fractional charge of positive 2/3 the elementary charge, negative 1/3 the elementary charge for a down quark. They all have spin numbers of 1/2. Here are your anti-quark equivalents. And you have, just a bunch of different quark configurations for your mesons. Your mesons are your hadrons with a quark and an anti-quark. Your baryons are your hadrons with 3 quarks and a spin of half integer. Okay, now we also need to just come back and revisit beta positive and beta negative decay from a quark perspective. So we're going to break it down to another level. Beta decay involves the emission of a lepton. So a lepton can be an electron or a positron. It occurs via the weak nuclear force. Again, the weak nuclear force is the one that's responsible for changing a proton to a neutron and vice versa, which is something that does happen in beta plus and beta negative decay. Okay, so let's revisit beta negative decay. In beta negative decay, if we break it down to the quark level, what happens is a down quark in a neutron turns into an up quark through the emission of a W negative particle, which is the mediator for the weak force. Okay, this statement's a bit confusing, so sort of break it down in terms of the equations. Next to the W negative particle decays into an electron and an antineutrino. Yes, let's look at this. Okay, in beta negative decay, there is a conversion in the parent isotope to the daughter isotope where you go from a neutron to a proton. Okay, we know that. We knew that from the previous lesson. Neutron to a proton. If it's beta negative decay, what kind of electron we get? The negative one, hence the electron. What kind of neutrino do we get? The one opposite of what would be the positive or normal one, which is the antineutrino. So that's how we would have written down a beta negative decay equation before. Now we're going to break it down in terms of like what's going on with quarks and our virtual particle. Okay, the quark configuration for a neutron is UDD. The quark configuration for a proton is UUD. So in the process where a down quark turns into an up quark, what does this? The conversion from a down to an up quark, it's your virtual mediating particle called a W negative particle. Okay, so that's responsible for turning a down quark into an up quark. Now, after this W negative particle does its job, and its job is to turn it down to an up quark, it then decays. And what it decays into is an electron and an antineutrino, which we often refer to as an electron antineutrino because it accompanies an electron. So if I write down the full equation in terms of quarks, I could say that UDD, which is a neutron, becomes UUD, which is a proton, and I also emit two leptons. We emit the electron and an electron antineutrino. Okay, this just shows how the virtual particle is involved in this process. How about beta positive decay? Beta positive decay involves an up quark and a proton turning into a down quark, and it does this by means of the W plus particle. After that W plus particle does its job, it then turns into the other two leptons you expect in the nuclear reaction. So that's going to be a positron and a neutrino. Okay, let's break it down. In beta plus decay, our parent isotope, we have a conversion from a proton in it to a neutron. So we have 11H to 10N. And we also emit a positron and a neutrino. So again, the way I remember this is what kind of electron is emitted in the beta positive? Well, the positive electron, that's a positron. What kind of neutrino? Positive, I think of as like the regular one. So that's just the regular neutrino. In terms of quarks, we can write it down as UUD, which is the quark configuration for a proton, gives us UDD, the quark configuration for a neutron. And what does this? What's responsible for taking an up quark and then turning it into a down quark? Well, it's my mediating particle, the W plus one, because the W plus one is involved in this radioactive decay. After that W plus particle does its job, it then decays into the two leptons I expect to see in beta plus decay. So that's going to be a positron, E plus, and it's also going to be an electron neutrino. So if we write down the actual full quark configuration for beta plus decay, it would be UUD, which is a proton, turns into UDD, a neutron, and it is accompanied by two leptons, a positron, and an electron neutrino, or you can just call it a neutrino. One thing just to note is when you're looking at quarks and nuclear reactions, conservation of charge needs to work. So if I wanted to, I could break down UUD into all my fractional charges and add them up. And both sides of the equation must have the same net charge. So conservation of charge still needs to be upheld when you're looking at writing down these interactions in terms of quarks. We're going to finish the course off by talking about one more thing, which is the standard model. You can think of the standard model as being like a heavily updated model of the particle theory of matter. So the particle theory of matter, which I don't know when you were taught it, I definitely teach it in my grade 7s, tells us that all matter is made up of the smallest particle that is called an atom. Nothing is smaller than an atom. Well, this clearly is not true. Okay, it's made up of much smaller particles. So what are they? Okay, so we'll worry about that in a moment, but the standard model likes to try to explain things in terms of our fundamental forces. So I said our first is the currently accepted explanation for the strong and weak nuclear and the electromagnetic force. You'll notice that one of my 4 fundamental forces is missing here. That's the gravitational one. The issue with the gravitational force is the mediating particle is a graviton. And as I mentioned, a graviton is a particle that we have not observed anywhere else outside of like just that mediating interaction. All the other mediating particles, like a photon or a gluon or the W plus W negative particle, we can apparently experimentally prove they do exist. But a graviton, not so much. It only exists mathematically in theory, so it's not part of the standard model. Okay, point 1 tells me that all matter is composed of 12 fundamental particles. Okay, as opposed to saying all matter is composed of the smallest particle called an atom, there's 12 specific fundamental particles. What are they? They're the 6 leptons. So 2 of those leptons are an electron and a neutrino. And the other one, I think, was like a tauon neutrino, a muon neutrino, and 6 quarks, where your 6 quarks are the up quark, down quark, strange quark, charm quark, top quark, and the bottom quark. Plus all their antiparticles. You'd have like 12 fundamental antiparticles as well. Point 2. The electromagnetic and nuclear forces are mediated by virtual particles. Okay, I addressed that in the previous lesson, albeit very poorly, where we talked about how it's the mediators that are responsible for how different particles interact with one another. So that's quantum field theory. 3, the weak nuclear and electromagnetic forces are both aspects of a single fundamental force. Apparently, if you're looking at a situation under if you're looking at a scenario where like you have like really high energy, I'm talking about like high energy in terms of like Big Bang conditions. Apparently, the weak nuclear and electromagnetic force behave like a single fundamental force. I don't know much about this theory, but there is a theory to describe. It's called the electroweak interaction theory. And again, I didn't talk about it at all. I noticed briefly that apparently at higher energy conditions, these 2 forces can actually behave like a single fundamental one. And our 4th one is the strong nuclear force between quarks is described in terms of the concept of color change. So again, I tried to explain that quantum property of color, although it has nothing again to do with color. Hence, like the whole thing with the anti-red. And that's a theory that's referred to as quantum chromodynamics. So you can see here just kind of like how like we break matter down. So we have a molecule that's made up of a bunch of atoms. Within an atom, we have our electrons that are fundamental, but our nucleus contains protons and neutrons. If we take a neutron or a proton, we can break it down into our quark. Okay, so our fundamental particles, your basic building blocks at the end of the day, would be your 6 quarks plus the 6 different leptons. Okay, that's it for this lesson on quarks. You can complete the assignment that's called Quarks. And that is it for Physics 30.